Welcome back, students. We're done with sections 1, 2, and 3. And now let's go to section 4 of this notebook, Properties of Scalar Product. What is the scalar product, by the way? We went through this in section 2. And here we go. Oops, wrong key. Sorry about that. Okay, there we go. Multiply each component, x1, y1, x2, y2, x3, y3, and so on, and add them all up. The result is a scalar, a real number. Vector times vector is a scalar. That's scalar product. Let's copy and paste this thing down here. By the way, don't get confused with scalar multiplication. Scalar times vector is a vector. Multiply the scalar k to each component. That's scalar multiplication, not scalar product. Okay. First property is symmetry. X dot y is equal to y dot x, or commutativity. Is that clear from the definition? I don't know whether that's clear to you or not. In any case, you'll have to do it. I assigned it as a homework. Okay, let's go to the next step. Bilinear. What do you mean by bilinear? Let me explain it a little bit later. First one is the distributivity. We can separate this addition, vector x plus vector y, and you can distribute vector z to both x and y to generate the right-hand side. And then you can do the same thing here. You can separate this y plus c, the second part, and then you can distribute vector x so that we get x dot y plus x dot c. The third, I don't know what this should be called other than bilinearity, so let's not name it. Let's just go here and then explain that. I can take this scalar multiplication out and multiply it after taking that scalar product. Same thing here. I can take this scalar out and then apply it after I take the scalar product. By the way, being able to separate this addition like we did over here and then take the scalar out, those two properties are called linear property. That's extremely important property in this course. After all, this course is called linear algebra. Let me go back to this again. Separating the addition and taking the scalar out. That kind of property is called linear. Linear. But why are they called bilinear? Because it applies to the left-hand side of this dot product and also right-hand side of this dot product. Both of them. Here as well. Applies to left-hand side of that dot product and the right-hand side of that dot product. So we call it bilinear. Finally, positive definite. X dot x is always greater than or equal to 0, and moreover, equality holds if and only if it's a zero vector. Okay, these are four typical properties, four fundamental properties, and let's see. Do you have enough time to prove one of them? Let's try this, the first one. And again, the typical technique we use is proof by algebraic manipulation. And what is x dot y? Well, definition is right over there, so let's use it. And then in turn, this is equal to multiplying each component together and then adding them up. Okay, so far we didn't do anything spectacular. We just applied the definition of the scalar product. Now we have to do some algebra. And what kind of algebra are we going to do? We want to prove x dot y and y dot x are the same. So we're going to switch the order of those multiplication. So we're going to do exactly that in the real number arithmetic. x1 times y1, I'm going to rewrite it as y1 times x1. Switch the order of multiplication in real number arithmetic. And of course, that's true because in real number arithmetic, we have the commutative law of multiplication. So this and that are the same. Now let's go back to the definition. This is y dot x and let's align the equalities and then we are done. By the definition, the final expression is the same as y dot x, the right hand side. So here we go, the full proof. And please note that this is very, very typical proof by algebraic manipulation. Start from the left hand side and apply the definition, some algebraic manipulation, really minimal algebraic manipulation, and then backtrace, and then we get to the right hand side. You can do something similar kind of algebraic work to this one, this one, this one, and that one. All those are homeworks. This one is a little bit different because we have to consider that moreover part. Okay, I'll leave that as a challenge for you. This part is not too difficult, just straightforward application. By the way, students with keen eyes will see that the second line is unnecessary. If you prove the first one and then use symmetry, then the same thing applies to the right hand side of the dot product. Same here. This one will turn out to be unnecessary. Prove this using the definition. Yes, you have to do that. And then apply symmetry, and then this follows. Okay. All right. I guess I just covered everything that is essential. And now let's use the rest of this video for kind of optional topics. So if you're not really interested, you can stop here. So what about this remark 4.5, bilinearity? Bilinearity. Here we go. The bilinearity conditions 4.2 and 4.3 can be reduced to the following one-liner. So instead of just separating the addition like this and then taking the scalar out in two different conditions, put both of them together in ax plus by form. Second line, by the way, will turn out to be unnecessary. As I told you before, we have the symmetry. So if you establish this, the second follows immediately because you can simply change the order x and y, like change the order of this and that. And then, of course, you may have to change the characters a little bit, but that's just a minimal deal. So that's not necessary, so we're going to talk about only this one. Now, this remark is talking about it can be reduced, so these two are equivalent. In other words, you have to prove the equivalence. One implies the other, and also the other implies the first one. Okay, part 1 of the proof. We want to prove that these two, 4.2 and 4.3, imply this one. And part 2, we're going to go the other way around. Okay, part 1. How do we prove this? Start from the left-hand side and then apply 4.2 and 4.3, and then we have to get to the right-hand side. Let's see. Can you do that? So somehow we have to work something out. And then something. And then in the end. And then we want to get to the right hand side. And this is something we want. Of course, we'll have to fill in all these inside. Okay, let's go ahead and do that. How do you fill those in? Using 4.2 and 4.3. We'll do this. Put I'm going to set A and B both as 1. Oh no, excuse me. Excuse me. This is wrong direction. Excuse me. I was thinking about part 2 of the proof. Excuse me. I'm not using this. I have to prove this. Okay. All right. I'll use 4.2 and 4.3. So let's use 4.2 first. Distributivity first. So AX and dot product of Z. Not enough space. Put some space so that I can easily read. Okay, and then BY times Z vector Z. So what did I just use? I just used 4.2 distributivity. And then let's apply 4.3. I can take the scalar out. So from here, I'll take A out. So A times, now this is X dot Z, and these are all vectors. And then that 2 is a vector. And then from here, I can take B out. And this is a vector. And that's also a vector. And is that what we wanted to prove all along? Yes, indeed. We started from the left-hand side and applied the distributivity, and then take the scalar out twice, one for A, one for B. We get that. So that completes the proof. If you open up this notebook, I put proofs for both of them. Not only this one, but that one as well. But as I told you before, that's not really necessary. Okay, we are done with one direction. And let's do the second direction. Assuming this, we have to prove this one and also that one. Okay, let's prove the first one. So basically this is what you want. Anyway, I don't know how many steps will go in there, but eventually after doing something, we're gonna get that. That's what we want. Okay, let's do it. That Let me rewrite it. That can be rewritten because it has rewritten in that kind of form, like this. 1x plus 1i dot c. If I put a and b both as 1. And then we can apply this. I can take this 1 out. 1 out. So 1 and then x dot c and 1 times y dot c. And is that what we want in the end? 1 times any number. No change because 1 is multiplicative identity. So we do get the right hand side. So did we prove this successfully? Starting from the left hand side, applied appropriate algebraic manipulation, and then got to the right hand side. Well, really minimal algebraic manipulation because we are just using this for very special a and b values, both equal to 1. Okay, we are done with one of the two. One more. We don't have to bother the second lines because of the symmetry, so we're going to do this one and that one. That's complete. Okay, let's work this one out. Okay, so basically this is what we want. From here, anyway, work, and then this is what we want as a right hand side. Okay, alright, what kind of work do we have to do? Okay, let's rewrite this thing in this form. We already have a, but we don't have this b part. So let's write like this. Zero, and then let's see, some other character. If I put c, then it may cause a bit of a confusion because of the order. So let me just use another character. Okay. Adding 0 doesn't change anything, so I didn't do anything spectacular yet. And then let's apply this rule. I can take a out. Okay, I'm going to do that. And I can take b out. B is 0, so I'll do that too. So a times x dot y and then b, but that's 0, so it's 0 times w dot y, and both are vectors. So let me put these arrows, and let's see, 0 times anything is 0. So as a matter of fact, that's 0, and excuse me, that's 0, and then this 2 is 0. In the end, what do you get? Just that part. And did you successfully prove this using that? Yes, we did. We use another character, but well, it's just choice of character, no problem there.